All right, so welcome back to part 3 of lecture 17. Now that we have established that the least squares estimator are no longer efficient if you have spatial dependence in model errors, and that by consequence the least squares estimators are no longer blue. So then, what we do is we move on to a new, estimation strategy and to what we call as a generalized least squares estimators. So in general, what we have done is we have moved from a specialized variance covariance, structure for model errors that is in front of your screen, which is the one where the variance of each delta Si is exactly the same, which is sigma squared, and the covariance between these deltas, that is model errors at two different locations, is 0. So the off diagonal elements are 0 and that diagonal elements are exactly the same, which is a constant sigma squared. We have moved to a generalized variance covariance structure where we introduce non-zero off diagonal elements, which are nothing but the covariance, non-zero covariance between errors of two different locations. When rho is greater than 0, what it is exhibiting is a positive spillover from the unobserved factors onto each location of interest. So each location of interest is getting a positive spillover from its neighbor. If the neighbor is nearby, the spillover is strong, which is sigma squared rho. If the neighbor is farther apart, the spillover decreases in intensity by a factor of rho to the exponent of how far apart they are. This is a simplistic, however very realistic type of a spatial dependent structure. That's what you would expect in space when you see clusters, in a locality of equal, intensity. But as you move away, there are clusters of different intensity. So there is less dependence on values that are farther apart than relative to the values that are closer together, right? So this simplistic starting point, variance covariance structure is powerful enough to capture such a real world spatial dependence structure. In the presence of this structure, when it is known, exactly known, when we are able to exactly write down what our rho, variance covariance matrix is, which is a n by n matrix, which is no surprise. We are working with n sized columns for deltas and for r's for p's. So basically, we have an n sized column for each data set. We have n observations, and the variance covariance matrix is n by n, right? In this case, the GLS estimator is written as x prime omega inverse x times x prime omega inverse y. Now the beta hat is written as in a matrix form. Remember, till now we have written it all in scalar form, right? Just to do a slight translation, so if I were to write a ordinary least squares, which is the non-generalized form, I will write beta hat ls equals x prime x inverse x prime y. Okay. Now, what is to be understood here is that when we move from least square to GLS, what is happening is that in my estimator, I am somehow normalizing or weighing for this omega inverse, matrix, right? Now, in case of least squares, I could envision doing the same. I mean, I could write, sigma squared in inverse and sigma squared in inverse as a sandwich. And what will happen is, if you solve it, what will happen is that these two terms will actually cancel out. But when the matrix is a bit more complex, that is omega, this cancelling doesn't happen. So the generalized least squares makes the least squares formulation a special case of itself, right? Now I'm going to just get rid of this sandwich form just for our convenience going forward. If you want to see the correspondence between the scalar form and the matrix form, you can just we can just write down the scalar form and you will start to see it. So beta hat 2ls was equal to summation n equals 1 to n p minus p bar r minus r bar divided by summation 1 to n r minus r bar. sorry what the spelling mistake, minus r bar squared. Okay, so now P is my y and x is my r, right? So this numerator directly corresponds to x prime y, whereas the denominator directly corresponds to the x prime x inverse. So the matrix form is just a concise form of data, right? The matrix X, what is matrix X, what is matrix Y, all of that, let's look at it with our example going forward. But here I just want to sort of provide you a functional form for beta hat GLS and how it is different from the beta hat LS, right? Beta hat GLS explicitly accounts for the complex variance covariance structure, which accounts for spatial dependence, by the way, into the estimator definition by itself. Okay, so for our example, right, for our example, that is, you know, P Sn equals beta 1 beta 2 r Sn plus delta Sn with covariance delta u delta v equaling sigma squared rho u minus v, where rho is between 0 and 1. So it's positive but less than 1, greater than 0, right? So it's a positive spillover. If rho were negative and it were, you know, then it would be negative spillovers. That is to say that if I see a high value at a given location in its neighborhood, I am likely to see lower values. So spatial autocorrelation can be positive as well as negative. We will probably, in most cases, you will find you know, cases of positive autocorrelation. It depends really, right? Okay. Okay, so now when I say beta hat GLS as x prime omega inverse x inverse x prime omega inverse y, what I am saying is that x is nothing but a vector of 1s, that is this coefficient 1, and the r's. Okay. Now I have data where I have data on n locations. So I have, let's say, location S n, so S1, S2 till Sn, and for each location I have a value p, which is, let's say, p1, p2 all the way till pn, and then value till r, that is r1, r2 till all the way till rn. This coefficient of beta 1 is a coefficient of this value 1, which is a constant. So I have an intercept which is nothing but a column of 1s. So this column 1 is what this 1 is representing. So we'll draw it as a bold just to say it's a column vector, and obviously its size is n by 1, and so is the size of this vector r, which is also n by 1. Hence x is nothing but n by 2, and y is my vector of prices, which is again a n by 1 vector, right? So y is nothing but, you know, pi's going from I to equals 1 to n, organized as a column vector. So y itself is a n by 1. So what I have is a x transpose is going to be 2 by n. Omega is a n by n, its inverse. Inverse of a square matrix is the size of the matrix itself, and x is n by 2. X prime is 2 by n. Omega inverse is n by n, and y is n by 1. When I multiply these, of course, you know, there is conformity. So there we go. So we have 2 by n, and again I have a 2 by 2 matrix. So the first matrix is a 2 by 2 matrix. The second matrix, let's evaluate, is going to be again 2 by n and a 2 by 1. So the second matrix is a 2 by 1 matrix. Again, they are conformable, and the final matrix is going to be a 2 by 1, right? So that means that beta by itself is a 2 by 1 matrix, implying that it is comprising beta 1 hat GLS and beta 2 hat GLS. Okay, so I'm as if I am very concisely able to, summarize the solution for beta hat GLS in this 2 by 1 matrix. So we are moving away from the scalar representation to a vector representation or matrix representation, but they are really all translate really easily, right? So it's not like it's not so hard at the end of the day. Okay, so now, okay, so we have our estimator beta hat GLS. We know that it's a random variable. Why? Why? Because, it is itself a function of this random variable y, which is nothing but the prices, right? X's are non-random. What is in the variance covariance matrix are non-random. Sigma squared and rho are model parameters. But what is random is y, right? So that means beta hat GLS is also random, right? Another thing is beta hat GLS is linear in y. It's very important to see that it's linear in y because all you are looking at is a constant here, a constant here. So basically what we are looking at, somehow beta hat GLS being written as a constant a times y, right? You can reformulate this whole thing in that format and view this in this format. So the y is n by 1, and here I'm going to have a 2 by n matrix A, where A is nothing but x prime omega inverse x prime omega inverse. Okay, interesting, way to view these objects. So having understood that, I can write down the variance of beta hat GLS. Of course, the variance is conditional on the data that is given to me, that is R. I'm just going to use X just to be, keep myself in the same general format. This is going to be x prime omega inverse x. Okay, sigma squared is the model parameter. It's coming from right here in the variance covariance structure. I have my sigma squared. It's the same sigma squared here, right? It's a scalar entity, a constant. And inside I have x prime omega inverse x, the whole inverse. Sorry about that. Okay. Now let's evaluate the size of this matrix. I have 2 by n, n by n, and n by 2. So I have a conformable 2 by n, and then finally I have 2 by 2. So the variance of this matrix is a 2 by 2. So the variance matrix is 2 by 2, which should not be surprising because at the end of the day, it's the variance covariance matrix of beta hat GLS. So variance of beta 1 hat GLS is the, and variance of beta hat 2 GLS are the the diagonal elements, and the off diagonal elements are nothing but the covariance of beta hat 1 GLS and beta hat 2 GLS. Okay, this is a symmetric matrix because the covariance of the flip order, which is covariance of beta 2 hat and beta 1 hat, is exactly same as covariance of beta 1 hat comma beta 2 hat, right? So this is exactly the same here. So covariance of beta 2 hat and beta 1 hat. Okay, now so we are done, right? So if we have a spatial dependence, a structure with spatial dependence, rather than working with beta hat LS, that is the ordinary least squares, we should work with beta hat GLS, which is the generalized least squares format. However, there is a slight issue, right? There is a slight issue. The issue is that the above formulation is assuming the knowledge of omega, right? This above formulation has assumed the knowledge of omega. However, in real world, cases, in real world situations, we may not know omega. In fact, we will not know omega a priori, right? However, in most applications, we will not know omega a priori. Okay. In such a case, in such a scenario, we have to, back out omega from the data itself. We suspect spatial dependence. So we know there is a general, there might be a general, variance covariance structure going on. We are also aware that if there is a general variance covariance structure going on with the non-zero off diagonal elements, or even perhaps, non-constant diagonal elements, then, we know for a fact that least squares is not going to be efficient. So we must come to generalized least squares, but we do not know omega. Then what do we do? Well, what we then do is called as the feasible generalized least squares strategy. Okay. So going forward in the next sort of slide, we are going to start looking at an example of how do you implement the generalized least squares estimation when in fact you are not aware of the exact omega spatial dependence structure through omega, which is the variance covariance matrix. Okay. Okay. So I am going to sort of title this slide as the feasible generalized least squares strategy in the presence of spatial dependence. Okay. So say we have data which looks like the following. Let's say we have data on P, which is the prices. We have data on the spaciousness of this housing entity at location N, which is R, and we have data on public amenities, let's say, which is A. Okay. So of course, we have price of house, right? We have the spaciousness or the number of rooms index, and we have a public amenities index. This could be, quality of schools in a neighborhood, or, that is attributable to that particular house in question, public parks. People care about parks when they buy homes, they care about school quality around that area, etc. and etc. Okay. Now we are, we are interested in the following model. In estimating the following, regression model. Okay, so we have P Sn equals beta 1. So I have the intercept beta 2 R Sn plus beta 3 A Sn, and finally the model error delta Sn, right? Such that we know that Sn is basically locations S1, S2, and keep going till S capital N. All of these are in the second two-dimensional real space, right? And we also know that this is not the complete model. The complete model is that we have covariance of delta at Si and delta at Sj, right, where I could go from 1 to n and j could go from 1 to n, is a general variance covariance matrix omega, right. So here what's happening is that we suspect spatial dependence in data, dependence in housing prices, right, because we live in the real world. So if we see housing prices with higher priced houses located in a cluster together, and lower priced houses located in another cluster at a different location, then we know that prices exhibit spatial dependence. Now when we have specified the systemic portion of this model, we have not specified spatial dependence in any way. So where is it all going to be? It's going to all reside in the error term, something that we could not or did not account for in the given model, right? So as an analyst, I suspect, as an analyst, we suspect that there will be spatial dependence in housing prices, right? But we do not know the exact form of it, right? We don't even know the approximate form of it. So we must use the data. Because my data exhibits it, then I must be able to back it out from the data, right? That is called as the FGLS strategy. So we will study this strategy in steps. So step 1, okay. Step 1 is run the least squares regression for estimating the price PSN as a function of RSN and ASN with intercept. Okay, so we don't know omega, so we can't really we can't really evaluate beta hat GLS. So all we are left with is beta hat LS. That is, we get to our beta hat LS, which is x prime x inversed x prime y. Remember, x now is 1, which is a n by 1 vector. We have r, which is again a n by 1 vector, just like data in an Excel column. And then we have a, which is again an n by 1 vector. Okay, so x by itself is n by 3, and y is nothing but the price vector, which is n by 1, and so y is also n by 1. So beta hat LS is made up of 3 by n and n by 3, so overall 3 by 3 inversed, which is 3 by 3, times 3 by n and n by 1. So I'm looking at a 3 by 1. They are conformable, perfect. I have finally a 3 by 1 vector. This is a 3 by 1. So what I have been able to back out is beta 1 hat least squares, beta 2 hat least squares, and beta 3 hat least squares. Now note that the beta hats, beta 1 hat least squares, beta 2 hat least squares, and beta 3 hat least squares are still unbiased. Okay, we have established in this lecture, at the beginning of this lecture, that even when there is spatial dependence, even when there is heteroscedasticity of the form of spatial dependence in data, it doesn't affect the unbiasedness property of a BLEU estimator, right? So it's still unbiased. So we are good to go as using beta 1 hat, beta 2 hat, and beta 3 hat as good guesses of true beta 1, beta 2, and beta 3, right? So using these, I'm going to propose that we obtain delta hat, Sn as Psn minus beta 1 hat Ls, beta 2 hat Ls R at location Sn minus beta 3 hat Ls times A at location Sn. Okay, so I can evaluate basically, I can evaluate it at each location. So, we know that Sn is as all S1, S2 all the way to S capital N. So I have a very good guess of also model residuals, that is the difference between the predicted value and the true value, right? So this is the true value, true price, which we observe in the data, and this here is my predicted value. Right? This gives me, now because beta hats are good to go, they are good guess, so is a predicted price a good guess because it's just a linear function, right? And so if I deduct this predicted price, which is a good guess, from the actual price, I get a very good guess of delta, which is delta hat SI. This is all happening with the least squares estimator, which we can work with, quite efficiently without even, worrying about the omega structure. So we suspected there is omega. We don't know it, so we are doing what we can do best, that is we can run the least squares estimator. The least squares estimator is falsely assuming that omega is sigma squared in. We know that. As an analyst, I'm aware of that. But with that in mind, I know I can still back out beta hats, which are unbiased in nature, right? So with these beta hats, I will now back out delta hat, Sn. The second step, step 2, is I must evaluate the stationarity of delta hat Sn. Okay. Now I want to evaluate this stationarity of delta hat Sn, because why? Because we will employ delta hats to evaluate spatial dependence through a variogram model. So in the next step, at step 3, I'm going to say that plot an experimental variogram. Okay, and for a variogram, we are well aware that we need intrinsic stationarity. We are well aware what is stationarity. We know that if we don't have stationarity, we can't really define a variogram. We also know that if we can get to the variogram, we will have backed out the data-driven spatial dependent structure that we really need to get to omega. Okay, now, so that's why, before we go on to jump onto step 3, we should take a step back and evaluate whether, my delta hats are stationary. At the minimum, I should worry about, can there be regimes of different mean values of these error terms given the data I have? Can there be some kind of spatial trend that I should filter out? So if the data you suspect them to be non-stationary, you have to first create this filter, construct this filter, which you will deduct from the delta hat values. And then finally, the residuals that you work with, you will then estimate a variogram. So I'm going to assume in step 2 that we have assessed that the delta hat values are stationary, and we are going to move forward with that knowledge. Okay, again, stationarity is a decision and it's not a hypothesis. Please go back and refer to the lectures where we studied stationarity. Okay, we are going to plot an experimental variogram for delta hat Sns. Okay, that is to say that I will calculate 2 gamma h, which is going to be nothing but 1 over the count of values separated by count of pairs, location pairs separated by a lag of h, and I'm going to go from I equals 1 to n of h. This is the set that consists of all the pairs, location pairs separated by a value h, a lag h, delta hat Sn minus delta hat Sn plus h, right, squared. We have seen this. We've seen this, multiple times. We will again see it very soon because you're going to get to the hands-on exercise, in a couple of, lectures. So we are coming to the variogram, experimental variogram, the variogram cloud, and so on and so forth, right? If you want a little bit more familiarity, well, we had plotted, the variograms. We had seen the variogram cloud, and basically, you're looking at something like this, right? So you are looking at these variogram values at different levels of, lag. So you vary h, h itself is a variable. It's a spatial lag, right? So with this H, you figure out, you can figure out some very important properties. It's to say that to any value, its nearer values are highly, they are highly correlated, or there is high degree of covariance, and as we sort of leave that location, the covariance dies out, eventually, reducing to a large scale variation in the data, where we have nothing to learn from in the no spatial correlation regime or range. Okay. Step 4 is going to be natural. I'm going to fit a variogram model. Right. So we saw variogram models. You can refer to the lecture notes. We looked at the spherical variogram model. We looked at the exponential model and several others. So I'm just going to leave it at that. Right. All of this is doable through a software. So variogram, we know how to estimate a variogram, theoretically. Now, we will, and the hands-on exercise we will be able to estimate the variogram model. Right. So when you do that, you obtain what is called as the range, you obtain the sill, and you obtain the nugget. Typically we obtain these entities. The range is nothing but the extent of spatial dependence in data. Okay. Sill is the large scale variance. Sill is the large scale variance, and nugget is the micro scale variance or variation variance. Okay. These parameters now start to ring a bell of how omega will look like. So omega, which is the unknown, which is what I am after, right? This is the unknown variance covariance that we are after. Is this omega. Now sill is going to be large scale variance. So sill is something that should fill up my, sill is something that should fill up my, the diagonals. The range is where the extent of spatial dependence. So if for any h greater than 0, let's say there is no spatial dependence. Let's say we have a model, where it's a special case, but the variogram shape is such that it just dies out after leaving h very quickly, right? In such a scenario, you will have a case where off-diagonal elements will be 0, because that's what spatial dependence is telling us. If we know that after a certain point, starting from S1, after a certain point after the range, there is no spatial dependence, so all the covariance factors will be 0. The ones that are non-zero can also be backed out from the variogram model. Okay. So we are now starting to fill in this omega from what we have learned here in step 4. So let's do that as step 5. Step 5 is just, we are saying, evaluate the data driven variance covariance matrix, and we are going to call it omega hat, because it's a data driven device. Omega hat is now going to be C0. C0 is the sill, right, the large scale variation. It's going to be C0s, C0s, C0s. And here I have C S1, S2, C S1, S3, keep going, C S1, Sn. Okay. Let me just, okay. Now C S2, S1, C S2, S3, all the way C S2, Sn. Similarly, I can fill these up CSN S1, CSN S2, keep going till C0, and that's how my variance covariance matrix will look like. Where we know that the value gamma h that we have evaluated from the model in step 4, right, from step 4, this value is equal to C0 minus CH. I can write this as or gamma S1 minus S2, right? I can say Si and Sj, just generalize this, equals C0 minus C Si and Sj, nothing but the covariogram, the covariance between values at locations Si and Sj, where we know that I goes from 1 to n and j similarly goes from 1 to n. So the variogram provides me a data-driven analog of omega, right? If you want to sort of, get a refresher of where this matrix is, you can refer to the redundancy matrix in your notes from when we covered Kriging estimator, the spatial interpolation estimator. Okay, we explicitly wrote this matrix. It's called as a redundancy matrix, and we even called it R. Okay, so you can go back and look at R. It's exactly the same matrix that we have used for spatial interpolation. The beauty here is that now we are integrating the same idea that we used for spatial interpolation into spatial regression, and we are getting away with the inefficiency of our least squares estimators by doing so. Okay, so as step 6, I'm going to evaluate what are called as the feasible GLS, that is what was feasible given the data. We didn't know the exact omega structure. Okay, estimator as beta hat FGLS equals x prime omega hat inverse x prime omega hat inverse y, and the variance of beta hat FGLS is given as x in transpose omega hat inverse x, the whole thing inversed, right? So these are called as the feasible generalized least squares estimators. They are unbiased and they are efficient in the presence of spatial dependencies in the model errors. So beta hat FGLS is unbiased and efficient in the presence of spatial dependence in the model errors. Okay, this is very interesting. As a last bit of this particular lecture, we can evaluate the size of this beta hat matrix. So we have a k by n. K is the number of regressors. Here it was k equals 3, right? For special case, k equals 3 for our special case example, right? I'm going to say that this is n by n, this is n by 3, n by k. So I'm looking at a k by k. Here I have again a k by n, a n by n, and a n by 1. So I'm looking at a k by 1. So overall I'm looking at a k by 1. So I have a vector k by 1, which is nothing but an estimator for beta 1 hat FGLS, beta 2 hat FGLS, right, all the way till beta k hat FGLS. Okay, this is a very general form, and you can show, now you should show that this is going to be a K by K matrix on your own. Okay, so that's all I really wanted to cover in this lecture, but I guess it's very clear that variograms that we have spent so much time on, and the idea of stationarity is completely integrable with the regression modeling, right? And this is very powerful because we have studied variograms at quite a length. So now we are also empowered to estimate efficient regression models in the presence of spatial dependence in data. Okay, so I hope you enjoyed this lecture, and I will see you next time, where we will then, relax another assumption of our classical regression model. Okay, thank you very much for your attention.